Alright, hi guys, welcome to your Chapter 21 Statistics video. This video is going to further extend off of hypothesis discussion and hypothesis testing discussion and try to bring new meaning to that. This is exploratory. It's not easy stuff. This is not easy stuff to understand, but when we really dig into this, we're going to be able to understand hypothesis testing so much better. And the nice thing about this is that even though you're going to see some concepts you've talked about before represented in a new way, in a couple new concepts, there is no true new math here. So like I told you guys before, I think that probability, chapters 14 through 16 that we covered at the end of semester 1 and the beginning of semester 2 really has the hardest math. But meaning is really important in this chapter. So let's see what we can do here. All right, what you've got represented here is a bell curve. This bell curve is centered on P naught, the null hypothesis assumption for a population proportion. P naught, or P sub 0 is another way to talk about it. And also on this bell curve, you guys can see it, but my VGA cable is dead, so I can't see the red here. You've also got P hat, so that's a sample proportion, which, as you remember from a hypothesis test, that sample proportion is used to either build a case for or against the null hypothesis assumption that that circled population proportion is true. Remember, too, that the bell curve represents how, assuming the null hypothesis population proportion to be correct, that is what the bell curve is centered on, how sample proportions are going to behave of the same size. So sample proportions of size 100. Obviously, again, let me just draw some things here. So you would expect to see p hats often in this range here. Those sorts of p hats would occur frequently, again, because the height of the bell curve is greatest in that range. We would be less likely to see p hats, sample proportion values, in here. That's the meaning of the bell curve. All right, so what we need to talk about really is what the p-value represents. As we sort of left the discussion off in Chapter 20, I told you guys, use as a good rule of thumb that if you have a p-value that is less than or equal to 0.05, that would be that you would see a sample proportion behave the way you did for the hypothesis test you conducted 1 in 20 times or less than 1 in 20 times. That p-value we used when it was that low to reject the null hypothesis, and if you had a p-value greater than 0.05, we said, oh, okay, well, it's not that unlikely that we would see a sample proportion behave the way that we did, given this circled p naught is true. So we're going to say we fail to reject the null hypothesis. So one misinterpretation that comes up a lot from that is that you guys might think, oh, well then the p-value is just the probability, the p-value is just the probability that this circled null hypothesis population proportion is true. Because when our p-value is low, we reject the null hypothesis, and when it's relatively high, we accept the null hypothesis. But that is not what the p-value means. The p-value actually is the probability, let's see, do I want to use red? No, whatever. Probability that your sample proportion would be at least this extreme, given that the null hypothesis population proportion is true, given that this is the case. Remember, because we're using that circled p naught to represent how all the samples of a population are going to behave. So the p-value is not the probability that the circled p naught is true, it's the probability that a sample would behave as we saw it do, or more extreme, given that the null hypothesis proportion is true. So that's an important distinction to make here. All right, wanted to cover that for you guys real quick. Second thing, this goes back to what Chandler had asked about when we first started talking about chapter 20 stuff, and that was, well, what's going on? Actually, let me start on the first slide here. So this p-value thing, it seems awfully subjective. That was basically the argument. Like the whole, when do we accept the null or reject the null hypothesis? When do we fail to reject the null hypothesis? It seems a little arbitrary, and you're right. So one tool we have to sort of combat that, basically, I want you to think about the 4 steps that are included in a hypothesis test. Remember that you set up the hypotheses first, not a long step. Secondly, you make sure the conditions are met and specify the hypothesis testing model that you're going to use. Then you've got the mechanics, that's the guts, that's where the math comes in your conclusion. In the second step, I want you guys, along with where you would say, I'm using the 1 proportion z-test to specify what's called a significance level. And that is synonymous with alpha. Alpha is your significance level. Now what you're doing when you specify significance level is you're saying, in advance of performing the mechanics of the test and seeing whether or not you accept or reject the null hypothesis, you're saying, okay, at this cutoff value, at this alpha level, I am going to reject the null hypothesis if my sample is somewhere in here. If the probability that the null hypothesis proportion would explain my sample, my p-hat, my sample proportion, less than 5% of the time, if alpha is set to 0.05. Meaning that, of course, that with alpha, this blue bar being your cutoff value, if your p-hat is to the left of that in a one-tailed test, where you're checking for the alternative hypothesis to see if the true population proportion is greater than the null hypothesis proportion. Well, if p-hat falls to the left of this blue cutoff value, then you would say, okay, we don't have enough evidence that the null hypothesis is false because our p-value, in essence, is greater than 0.05. So you're checking, what you're checking really is that blue alpha value that you've got here against your p-value. 0.05 is a really common significance level, a really common alpha value to do a test with. You could go even more extreme. You could say, okay, let's check to see if when I'm checking against an alternative hypothesis that the true population proportion is greater than the null hypothesis proportion, let's check to see if our p-value is less than or equal to 0.01. I didn't mean to do that. So we would have to reject the null hypothesis, you would have to have a p-value for your p-hat of less than 0.01. So that means that, or equal to 1 in 100 times or less than 1 in 100 times, you would have the null hypothesis proportion actually explain the sample proportion you've got. So again, if your p-hat falls to the left, that would mean that you would fail to reject the null hypothesis. So again, you're checking with the significance level, you're checking your p-value against that predetermined alpha value, that predetermined significance level. If your p-value falls at or below that alpha value, you reject the null hypothesis. If your p-value falls above that alpha value, then you fail to reject the null hypothesis. So we've looked at what, diagrammatically here, what an alpha value, or where the alpha value would be in a bell curve when your alternative hypotheses were both one-tailed tests with where you're checking against the alternative that p, the population proportion, is actually greater than the null hypothesis proportion. All right, so a couple other diagrams to hopefully cement this significance level thing in. And it may not be after that. I fully expect to have some questions on this. If your null hypothesis was that the population proportion is like 0.60, and you're checking against an alternative that it was lower than that the population proportion is actually less than the null hypothesis proportion, your significance level, your cutoff, would just fall to the left of the bell curve. So again, if you had a p hat over here to the right, you would fail to reject the null hypothesis because the probability... Let me back up. I don't want to do the right just yet. Let's look to the left. So if you have a p hat value to the left here, you would reject the null hypothesis because the probability that the null hypothesis proportion would actually explain these findings would be less than 5% of the time for this sample. So it would be less than 1 in 20 times you would see a sample proportion that's behave this way. Again, if the sample proportion fell to the right, that would mean that over 5% of the time, over 1 in 20 times, you would see a sample proportion behave the way that it did from the context of the problem, given that null hypothesis proportion to be true. All right, so you have looked at 3 bell curves so far, trying to show you where your significance level, where your alpha value would be when you're doing a one-tail test. First 2 bell curves were for the alternative hypotheses, where we're checking against a population proportion greater than our null hypothesis proportion assumption. And for the third one, the alternative hypothesis, again, that the population proportion is less than the null hypothesis proportion assumption. All right, so what happens with a 2-tail test in an alternative hypothesis where you're checking to see if p is simply not equal to your null hypothesis proportion? Well, for an alpha value of 0.05, you simply split that 0.05 in half, and you're checking for 0.025% of all sample proportions to fall within the window on the left and on the right here and right here. So if you had a sample right in here, remember that a 2-tailed test checks for the probability that it would be less than this over here or greater than its symmetric opposite on the other side. You would reject the null hypothesis because the probability that a sample p hat, oh, that's going to get messy, I'm not going to add that in, that a sample p hat would behave the way that it did given the null hypothesis is true less than 5% of the time. If you had a p hat right over here, again remembering that a 2-tailed test checks for area under the curve both to the right and to the left, you would fail to reject the null hypothesis because the null hypothesis proportion would explain the results that you see more than 5% of the time. So it wouldn't be too uncommon to see the results that you saw. All right, so significance level, what I'm not going to do in these notes is show you guys a context. We're going through a problem using significance level. We're going to do that in class together. I want to get through the big ideas in chapter 21 with these notes. So again, just remember for now, significance level is what you check against the p-value to help make a determination on whether or not null hypothesis is false, or if you don't have enough information to conclude that it's false. That first. And second, significance level and alpha value are the same thing. 2 ways to refer to the same thing. All right, so what we have here in this third slide is a table representing the way outcomes from a hypothesis test can occur. In the columns here, you have the 2 possibilities. You have either that the null hypothesis is true, that's one possibility, that the population proportion the null hypothesis is claiming to be the case is actually the case, or that the population proportion is something else, that the null hypothesis population proportion assumption is false. So those are the only 2 things that can occur. Either P is what the defendant claims it to be, or P is not what the defendant claims it to be. Well, when we conduct the hypothesis test, we can make a conclusion one of 2 ways. We can either, as you know, reject the null hypothesis, or I did not mean to write accept the null hypothesis, or fail to reject the null hypothesis, quote unquote accept it. So when is that a problem? Well, it's not a problem whenever the null hypothesis is false and we reject the null hypothesis. That's a correct conclusion. That's something that we want to actually have happen from our hypothesis test. That we want to see that occur. Or, if the null hypothesis is true, the null hypothesis population proportion is actually the population proportion, and we accept that, and we've got another correct conclusion. But here in blue, you've got the two big errors that we can make in hypothesis testing. A type 1 error occurs when the null hypothesis is true. The defendant's argument is actually legit, but we reject the null hypothesis anyway. Looking back to last slide, check out the first bell curve here. Let's assume that P naught is actually the population proportion, but you have your sample falling to the right, in this case, of your significance level. So you would actually conclude the null hypothesis is false when you would be when it's incorrect to do so. That's a type 1 error. And the probability, let's look at this right here. The probability that you would commit a type 1 error is equal to actually your alpha. So when the population proportion is the same as the null hypothesis proportion, in this case, for this particular bell curve, 5% of the time you are going to reject the null hypothesis even when it is the actual population proportion. So the probability that you commit a type 1 error is, or think of that as rejecting the null hypothesis given that the null hypothesis is true, that is alpha. That is a percentage we've already looked at. So if you think of it this way. When you set up your hypothesis test, if you set an alpha value of 0.05, 5% of the time, you are going to be mistakenly rejecting the null hypothesis. It depends upon where your sample, though, falls. If you set an alpha value equal to 0.01, well, then only 1% of the time you would be committing the mistake of rejecting the null hypothesis, even though it's true. All right, so there's the probability of type 1 error. The probability of committing a type 2 error, that would be when you accept the null hypothesis, even though the null hypothesis is false. That we refer to as capital beta. I don't think the alpha is capitalized. I think that's a lowercase alpha. I think the beta is capitalized here. I don't know why the difference exists. But anyway, alpha, type 1 error. Beta, type 2 error. One way to think about this, type 1 versus type 2, because it's hard to memorize unless you have some simple way to remember it. Just remember that when we conduct a hypothesis test, we assume the null hypothesis to be true. That's the first thing we do. Similarly, the type 1 error, the first of the two errors, is the mistake we can make when the null hypothesis is true. So, probability of committing a type 2 error. I don't have a way to represent that to you just yet. We're going to look at that next slide. But for now, we just call it beta. And finally, the probability of correctly rejecting the null hypothesis, that would be the probability of rejecting the null hypothesis when the null hypothesis is false, we call the power. It's not always capitalized, but in these notes you'll see it always capitalized. We call that the power of the test. So we want high power, obviously, because power refers to one of the good, correct conclusions that we saw above. Rejecting the null hypothesis when the null hypothesis is false is this right here. We want to make sure our hypothesis test, again, has high power. All right, next 3 slides are the most interesting slides on this to me. And like I told students last year, if you can understand the next 3 slides, you will probably be doing very well in Chapter 21. It's really at the heart of the material. All right, so what you see here is 2 bell curves. I want you to focus your eyes first on the bell curve that is not dotted. So this bell curve that is not dotted represents how the sample, the distribution of sample proportions when the null hypothesis is being used. So you might have a sample fall in here, and if you've set up your alpha value to be whatever, then you would accept the null hypothesis, or fail to reject the null hypothesis if your sample proportion fell to the left of alpha. Similarly, let me take those away real quick. If you had an sample proportion over here, you would reject the null hypothesis because your p-value, the area under the curve right here, would fall below that of the alpha value that you have predetermined when you did your hypothesis test. All right, so remember that the alpha value is the probability that you commit a type 1 error. And a type 1 error, again, was the error that we can commit for when the null hypothesis proportion is true, but our sample actually behaves in such an extreme way that we falsely conclude that the null hypothesis is not true. That's the alpha value. Okay, well, this second bell curve here represents the distribution of samples that exists for the true population proportion. Remember, we're assuming the defendant's argument to be true when we look at the sample proportion that's given to us in the context of the problem. But it's entirely the case that there's some other population proportion that is correct, right? And if that's the case, when we have a, how do I want to write this? When we have an alpha value right here of, like, let's say 0.05, beta, the probability of a type 2 error, is going to fall to the left of that. Type 2 error, again, remember, is where we accept or fail to reject the null hypothesis when the population proportion is not that of the null hypothesis. Alpha and beta are interrelated this way. As you increase alpha, your significance level, the probability that you commit a type 2 error drops, right? As alpha goes to the left or to the right, if we increase it further, then beta, oops, excuse me, not to the right, to the left. If alpha decreases, you decrease your significance level, then you actually are decreasing, I'm saying this wrong. If you bring your alpha level up, which is to move it to the left on this bell curve right here, then you're going to actually increase alpha, increase your significance level. But that means the probability that beta occurs, the probability of a type 2 error, drops in kind. They always fall on opposite sides of your significance level fence right here. Power, right over here, again, remember, is the probability that you correctly reject the null hypothesis when the null hypothesis is false. So let's say this dotted bell curve right here is actually the true bell curve explaining how samples behave. If you have a sample all the way over here, a sample proportion all the way over here, then you're going to correctly reject the null hypothesis. All right, so alpha and beta are inversely related. If alpha goes up, then beta goes down. Again, that would look like, let me erase some things here. If alpha is going to the left on the bell curve, if we increase the significance level, that is the p-value we're checking against is actually increasing then beta is also going to go to the left, which decreases its probability. This guy is increasing, this guy is decreasing. Conversely, if you decrease your significance level, that means you're moving this fence to the right. And the probability that you commit a type 1 error, yes, it drops, but the probability that you commit a type 2 error increases. That means that you would be less likely, if you decrease alpha, you would be less likely to falsely reject the null hypothesis if the null hypothesis is true, and that's alpha, but beta is going up, meaning that if the null hypothesis proportion is not the true population proportion, then and something else is, then you are more likely to accept the null hypothesis even if there's another proportion out there that actually is the true population proportion. All right. The explanation was decent there. I'm sure I'll get more questions on that in class. All right. So what I want you to see on this bell curve, notice the width of the bell curves here compared to the bell curves here. So you've got, again, two bell curves, just like we had last slide, where the one that is dotted represents the population proportion, P, when the null hypothesis proportion is not true. That's this guy. That dotted bell curve is how samples are actually going to behave when the null hypothesis isn't true. P naught, again, that's where the bell curve is centered that would explain how samples behave if the null hypothesis is true. So what we have here is because the width of these bell curves is less here than it is here, we have, to explain that, increased sample size. Remember that when you build the standard deviation of p hat, how far from the mean you expect to see samples behave, that is equal to the square root of PQ all over n, right? So as n goes up, the standard deviation, as n increases, the standard deviation decreases. That narrows the bell curves, right? That means that 65% of the data is going to be falling within a narrower window than if n were small. Again, this bell curve has been shrunk. All right, so what does that do to alpha and beta? Remember, alpha, probability of a type 1 error, beta, the probability of a type 2 error. Well, it actually should decrease both. When you set your alpha threshold at, let's say, again, 5%, because both bell curves have shrunk, the probability of a type 2 error that you would correctly, or excuse me, not correctly, falsely accept the null hypothesis proportion when it is not true, and there's another population proportion out there that is true, drops because the bell curves have narrowed. Again, remember, when alpha goes up, beta goes down. When beta goes up, alpha goes down. They're still related, all according to this cutoff significance level that we have predetermined. So, in general, if I want to make sure the probability of type 1 and type 2 error is going down, I increase my sample size. The power of the test, the probability that I correctly accept the alternative hypothesis that P is something other than P naught, when that's the case, goes up as long as my sample size has increased. Because the power right here and beta together equal 100% of the area under this dotted bell curve. So if beta's going down, power's going up. As beta goes down, the probability of a type 2 error goes down. The power of my test increases. Again, power being the probability that I reject the null hypothesis when the null hypothesis is false. All right, last one here. Let's compare this slide not to the slide that just came previously, but to this one right here. The difference, notice that the bell curves here and here are at about the same width. I'm trying to simulate these two different diagrams having the same sample size in each. So the standard deviation, the width of the bell curves, is the same for both here and here. But the difference is that P and P naught, oops, my label goes wrong. This should be, let me correct that real quick. This should be P naught. The difference is the difference between P naught and P, the effect size, excuse me, the effect size has decreased. Here the effect size was relatively large. Here the effect size is relatively small. Well, what does that do to the probability of a type 1 and a type 2 error? Well, notice if I set alpha at 5%, it doesn't really change the probability of a type 1 error, but holy cow, did the probability of a type 2 error go up. Remember again, probability of a type 2 error, the probability that we mistakenly reject, or excuse me, accept the null hypothesis when there's another population proportion out there that is correct. So if I had a sample proportion fall right in here, when P is actually the true population proportion, not the null hypothesis proportion, I'm going to, I have just committed a type 2 error. This guy was true, but because P hat fell to the left of my alpha value, I accepted or failed to reject the null hypothesis when I should have. All because the effect size was so small. It brought the two bell curves together in such a way that the probability of type 1 and type 2 error rose up so dramatically, I made a mistake. So there are two fundamental things that are going to determine the probability that you make a mistake. Well, not a mistake. It's not a mistake in the hypothesis test. You make a false conclusion in your hypothesis test. You can perform all the mechanics right, but this can still happen. If the true population proportion is close to the null hypothesis proportion, then the likelihood of an error and a conclusion when we make the hypothesis test rises. Similarly, if my sample size is really small, we looked at the case when it's really big. The sample size is really small, the bell curves flare, they get some serious hits on them, and you're going to have bell curves looking like this, where, again, if you set an alpha value with bell curves that are really wide, your beta value goes up big time. So, that's our introductory sort of exploratory look at Chapter 21, where we're talking about errors and other good stuff. I will look at a problem with you guys in class next time.